let me just, I had a little glitch with my video here. So for problem 11, a probability is a measure of the likelihood of a random phenomenon or chance behavior, the absolute true. I'll go back for one more second, sorry. For problem 10, it's absolutely true. The linear regression line will always pass through the point x bar comma y bar, always. The problem 9, the total deviation is always the unexplained plus the explained deviation. And I think I didn't miss anything else. And for problem 8, it's the possibility of having an outlier. There is no pattern in this residual plot, and that says that the linear regression model is appropriate, and I think everything else was okay with the number 7. Okay, so moving on, I think we reached, where are we? 9 was fine, 10, yes, 10.
Should be on 12.
Okay, thank you very much, on 12. Good. Suppose you toss a coin 100 times, so this is problem 12. N equals 100 times. And you get 93 heads, and you get 7 tails. Based on these results, what is the probability that the next flip results in a tail? So we have to find the probability for a tail is 7 over 100, and the probability for heads is 93 over 100. Easy, right? Because I can divide by 100 is very easy, 0.93, and for a tail is 0.07. Okay, so calculate your own. And tell me what you get. And that's it. The probability for the next one to be a tail is, in my case, 0.07. Moving on. Okay, maybe we can finish. A probability experiment is conducted in which the sample space of the experiment is given to us from 1 to 12. So now they're saying that event E, and this is my page 5. So the probability of event E, we'll see. So event E is 1, 2, 3, 7, and 9. And event G, in my case, has 9, 10, 11, 12. Assume that each outcome is equally likely. List the outcomes in E and G. Are E and G mutually exclusive? So let's see. No, they're not mutually exclusive, because there is 9, outcome 9 is in both. They're not mutually exclusive. I don't know exactly what you have. So it says list the outcomes in E and G. So the outcomes E and G, in my case, what is in both, first and second, I only have 9. That's what I have. And they are not mutually exclusive. Do we understand problem 13?
I'm still a little bit confused.
Which part?
So at least for my problem, I don't share any numbers.
In that case, they are mutually exclusive.
Okay, so by list of outcomes,
In E and G is nothing.
okay,
And that's why your example shows a mutually exclusive.
okay, just wanted to see how
Very
that
good.
worked.
Yes, yes, because this is not what I have. Very good. Thank you. Moving on to 14. Let me know if you have questions. Find the probability of E or F. Probability of E or F. If E and F are mutually exclusive. So that if they are mutually exclusive, is the probability of E plus the probability of F. And they are given it to me. I have 0.34 plus 0.51, and the sum is 0.85 in my case. So I'm entering 0.85. And I'm checking the answer. They say it's correct. Moving on. Any questions before we move on to 15? The data on the right represent the number of live multiple delivery births, okay, in a particular year for women 15 through 54 years old. Use the data to determine the following. Okay. Determine the probability that randomly selected multiple birth for women, okay. Involve the mother 30 or 39 years old. Okay, I cannot do anything before I add them up. I need to find the total. Without the total, I cannot answer any question. So my numbers are 95 plus 512 plus 1634 plus 2825 plus 1841 plus 374 plus 111. Okay, so the total is what I promised to do is I will have to, because you don't see my data, I will have to print out my own review, write the solutions for you, and post them. Because I didn't think that they will, I knew that I just overlooked the fact that you're not going to have the same numbers with me. And of course, some of you cannot 100% follow. And that is my mistake, and I apologize for that. So I am going to print out this document and post it today with my own solutions. Sorry about that. I should have done that. I should have printed out and sent it to you so we can all work on the same problems. It's not going to happen again. My apologies. Okay, so between 30 and 39. So there are two groups between 30 and 39. And what I have, 2825 and plus 1841 divided by 7392. So this is between 30 and 39. And I had to add those two. 2825 plus 1841, and I divide by 7392. So the probability is 0.63. Determine the probability that randomly selected multiple birth for women 50. Okay. Okay. So the probability for not 30 through 39 is 1 minus the probability for 30 through 39. So 1 minus 0.63 is 0.27. Part C, so this was A, B, and now C. Determine the probability that a randomly selected multiple and so involved a mother who was less than 45 years old. So less than 45, less than 45. I have everything minus the top. So it's minus the last one. Minus 111 over 7392. Or you add up all of them except the last one. So it was easier to write, to determine 1 minus 111 divided by 7392. So the probability is 0.985. They do want 3 decimal places. Be careful. They want 3 decimal places. So 0.63, 0.631. So this is this. So 9 no, this is, what am I doing? So 1.63, 631. So I have 9, 3 from 9 is 6. Okay. Part D, the last one, determine the probability that randomly selected such and such involved a mother who was at least 20 years old. At least 20. At least 20. I will do again 1 minus the top one. The top one, which is 95 over the total. So 1 minus 95 divided by 7392. 3 decimal places, 0.987. Moving on to problem 16. The data in the following table, sorry. Show the association between cigar smoking and death from cancer for I have 138193 men. Okay. Click to view the icon to view the table. Here's my table. Died from cancer, did not. Contingency table. Which means the totals are crucial here. So the first one, never smoked. Cigar. And current. And my data, 605, 76, 110. I need to find a total right away. Oh, I missed. I'm sorry, I have to start from scratch. In the hope that I can finish as many as possible with you,
So you find the total for each category
yes.
and then divide it by the total.
Nope, nothing. I have to answer the questions. I cannot make a decision yet what I'm going to divide. Did not. I don't know. So never a smoker, cigars, and current. Okay, I have to copy my data again. The total has to be what they gave us, but I don't trust it. I have to check. This should be the total because that's what they're telling us from the beginning. So 605, 76, 110 in my case, 121, 797, 5742, and 9863. At this point I calculate 605, 76, and 110. And here I have 791. And then 121, 797, 5742, 9863. 137402. If these two do not add up to this, something is terribly wrong. So I'm adding 791, and I get that correct. So now across 605 plus 121, 797, 122402. 76 plus 5742, 5818, and the last one, 9863, 9973. I will add them up to make sure that I didn't make a mistake. 122402 plus 5818 plus 9973 Make sure that I get, yes, I did. Now I answer the questions. Ready? Okay, if an individual is randomly selected from this study, what is the probability that he died from cancer? That's our first question. Probability died from cancer. How do I determine that? It's this total, this that died from cancer, divided by the total. 791 over 138,193. Second one, cigar smoker. So the cigar smoker is this, right? What is the probability that the randomly selected from the study will be a cigar smoker? So that is 5818 divided by 138193. And we have to calculate that. I just want to finish the problem and maybe do another, hopefully. If an individual is randomly selected from this study, what is the probability that he died from cancer and was a current cigar smoker? Died and cigar smoker. Died and cigar is at the intersection, so that would be 76 divided by the total. Final question. If an individual is randomly selected from the study, died from cancer or was a current cigar smoker. Died or cigar. So died or cigar, we determined both, but we calculated 76 over this twice, which means is this plus this minus this. So 791 plus 5818 minus 76 divided by 138193. And remember, you have to perform the top in parentheses before you finally divide. Okay, Winston and Lana, are you there? I can't see you. You are. Very good. Thank you. Hello. Good. Okay, 17. Let's read 17. For a parallel structure of identical components, the system has to succeed, at least one of the components succeeds. Okay, assume that components fall independently of each other. Okay. Perfect. So we are looking at problem 17. So point 17, the probability is 0.17 of failure. So here's our first question. Complete parts A through C. Would it be unusual to observe a one component fail? Would it be unusual to observe two components fail? So for two components, so the probability for two components, because they are independent, it will be 0.17 squared. So when I calculate 0.17 squared, I get 0.0289 because they are independent. That's the rule for independence. Probably the parallel structure with two identical components. Okay. How many components would be needed in the structure so that the probability of the system will succeed is greater than 0.99? Okay, so first let's answer the first question. So would it be unusual to observe one component fail?
Yes.
Because the probability is 17%. Okay, I'm entering my 0.0289 to see to have an integer or a decimal, do not round. how many components would be needed in the structure so that the probability of the system will succeed is greater than 0.999? So I would say myself that probability of 17%